I'm Gilad Shainer, and I've been some time at Mellanox, developing networking actually for supercomputing, and now almost 2 years within Nvidia after the acquisition, and actually managed to even build some supercomputers ourselves, so that we actually use internally within Nvidia. So looking into supercomputing platforms, first, what is a supercomputer? Right? Is that just a collection of computers sitting in one room and forming something that we call a supercomputer? The answer is not necessarily. Meaning putting a multiple compute servers in one room actually create collections of servers, creating a data center in a sense. But in order to transform or move a bunch or a collection of servers to become a supercomputer, you need to have those servers work as a single unit. You need to create the infrastructure and create the mechanisms where those servers will work as a single unit, not just as a discrete components working each in its own pace. And therefore, you need to be able to connect those servers together in a network that enables very high throughput and extremely low latency, so the data that actually moves between those servers or move between CPUs, for example, or GPUs, is moving fast enough so those unit actually, or those compute unit actually behave as one big unit, becoming one big computer. And once you do that, you actually can look into running applications in a very parallel way in that sense, and be able to solve problems that you cannot solve on a single computer. Now, supercomputers are used for many applications out there. First, all the simulations that we're running, all the large simulations that we're running, is part of developing cars or designing cars, for example. And that goes from designing the engines and designing or doing the safety designs and running a lot of car crash simulations to figure out how to build cars which are safer. All the protections elements, even the air conditions in the cars, how that works, and so forth. Simulations are being used by energy companies to figure out how to actually bring energy, where to drill, how to develop green energy, and so forth, to design airplanes, to simulate climate and weather, to design almost everything that we use, to design everything from Coca-Cola bottles, for example, swimsuits that you're trying to actually reduce the friction with the water, and that's being used by the famous athletes out there. So essentially, there are simulations all around us, and those simulations require supercomputers in order to be able to run effectively and run quick enough. The AI or deep learning actually brought more applications that require supercomputing performance. The training, NLPs, recommenders, real-time processing, creating digital twins. It's a great application, and we see many more of those. And all of those require a massive compute power that you cannot achieve from a single computer, and that's why you need to build a supercomputer for doing that. Now, on the other side, we have a lot of other applications, for example, that not necessarily require a massive computing power. And those applications today we can run on the cloud infrastructures. And cloud infrastructures, some of those are trying to bring performance like a supercomputer, but in a general cloud perspective, you don't have the tight connections between the servers, and it's being used for other kind of applications. Now, as we're moving forward, we will see actually more application requiring supercomputing. We will see obviously AI that's going to go everywhere. And as AI is going everywhere, every company in the world will need to have a supercomputer by itself. So we'll have more users, and it's not just the research or designing of things or simulations, but we're going to do AI everywhere. So every company in the world will need to will need to have its own supercomputer or access to supercomputer. And with decreased number of users and increased number of applications, we will need to redesign supercomputing architecture. And the reason that we need to redesign supercomputing architecture is that when we build a supercomputer today, the most important part is performance. The most important part is performance that enable us to solve problems that we cannot do on a standard servers in that sense. And the more that we know, there is more complicated things that we need to solve, and actually we need to increase the performance capabilities or the performance capacities. So supercomputer is all about performance, and everything that may reduce from the performance of a supercomputer is something that you are trying to avoid. And therefore, if you look on supercomputing or supercomputer platforms being built in different places around the world, those platforms have no real security or isolations between users inside of them. Those platforms or the people that running those platforms actually need to trust the users. Because if they try to bring security, if they're trying to bring isolations, the same that exist in cloud infrastructures, that will add a lot of overhead. That will add a lot of overhead and can reduce from the performance capacity of a supercomputer by 25%. And it's something that you cannot tolerate in that sense. So actually, they need to trust their end users. Now, what happens with the increased number of users and increased number of applications? Suddenly, trusting users in the supercomputing world, it's not something that works anymore. And there was a good example that happened last year with the COVID situation, where multiple large supercomputer sites in Europe has decided to provide open access to their supercomputers to everyone that did any sort of research in bioscience. Anyone that asked to run bioscience simulations as part of the COVID-19, the fight against COVID-19, actually got access to those supercomputers. Apparently, some people that ask for access to run bioscience simulations decided at some point that probably doing Bitcoin mining is more interesting, and therefore those supercomputers had to be shut down for 2 weeks in order to clean all the mess. And that actually brought up the need to start bringing security, start bringing isolations, user isolations into supercomputers. And of course, with the growing number of application users, that will become more and more important. And therefore, we actually need to redesign the supercomputing architecture to make it more available, more accessible by more users, to be similar to a cloud infrastructure from the infrastructure services. And that's actually require some redesign of a supercomputer, because you want to bring isolations and you want to bring security, but you cannot give up on the bare metal performance of the supercomputer. So that's something that is being developed now, and I'll try to give you a little bit of information about that. So first, let's look at an example of a supercomputer. And within Nvidia, we built one ourselves. Actually, we built several, but we built one for our own usage. We need supercomputing power. We need supercomputing power because we're actually developing applications for AI. And for developing the technologies that we need within the GPUs, within the networking, we need to simulate a lot of things. So actually, we also need the supercomputing power, supercomputing performance power ourselves. And we built a system which is the number 6 on the top 500 supercomputing list It's number 6, so it's the number 6 fastest supercomputing in the world. That system sits in California, in Santa Clara, and it's the fastest industrial system in the US. The system is being built using the Nvidia DGX nodes, the DGX systems. DGX system, you can see that it's in the gold, every gold box there. It's a DGX box. It has 8 A100 GPUs inside, and it also includes 800 gigabit, 200 gigabit per second network device to deliver the needed bandwidth into the GPUs or in and out to that box. So we call that supercomputer, we call it Saline. That's the name of it, and it includes the almost 4,500 GPUs inside in a 560 DGX systems. There is a networking infrastructure that connects everything together, very fast networking. So think about, there are eight connections of 200 gigabit per second, and that goes to each of the box. So every GPU is a 200 gigabit per second pipe in an extremely low latency network that's called InfiniBand. And in the middle, you can see some of the switches here that create the infrastructure here. So we're talking about 850 switches, huge amount of storage, and a great performance capacity that system brings us. Now, as we're building those systems ourselves, we actually can provide reference designs that enables people to copy what we did and be able to build a supercomputer in 3 weeks. In 3 weeks. Typically, it takes several months to build a supercomputer, putting all the servers, putting the infrastructure, testing everything, and bringing it up. That could go from 3 months to 6 months. And therefore, bringing the reference design, complete reference design from our side, as that represent how we did it, we actually enable people to build such supercomputers in 3 weeks or a few weeks. So it looks like, in a sense, if you're looking on the connectivity inside, and this is an example of a 1,000 GPUs pod, and of course that can be structure in any size. There are all the compute nodes. So in this case, there is a DGX nodes. It can be replaced by any other server, for example. And then there is the storage nodes as well. In our case, every DGX has 8 GPUs, the A100 GPUs, and then there are 8 200 gigabit per second ports coming out of each of the DGX node. Those connections are connected through 3 tiers of switches. 3 tiers of switches. There are switches that called leaf switch, which connect directly to the nodes. And then there is spine switches, and then there is core switches that actually create the full networking infrastructure. And for our systems, we decided to have a separate network for the compute side, for the compute communications between the GPUs. And then there is a parallel network that does the fast storage access, that enables storage to be accessible by the nodes. Those switches are extremely low latency switches. Every switch here runs in around close to 100 nanosecond. 100 nanosecond latency. And latency, being extremely low latency, is important because you want the GPUs, for example, to think that everything sits in the same node. Everything is very close to one another. So you can move data between GPUs in a very fast way. So there is no delays. You don't cause one compute element waits for another compute elements and so forth. You want all of those compute elements to work in a very synchronous way. So they run the compute, they do fast communications, and then continue with the compute and so forth. So this is how a supercomputer looks like, even in general way. Compute nodes, and then a fast network that connects between them. There are multiple options, sorry, to how to connect those switches together. What's being called multiple or different kind of network topologies. For the superpods, for example, for our systems, we decided to use what is being called multi-rail closed fabric. And multi-rail means is that we actually create a fast connectivity or direct connectivity between the same GPUs across different nodes. So for example, if we have 8 GPUs in every DGX, GPU1 connects directly to GPU1 on the other DGX, to GPU1 on the other, on the second, third DGX, and so forth. And then we combine everything together. In general, one can build different kind of network topologies, from fat trees to dragonflies to toruses and so forth. Depends on the applications. So you actually can tailor a topology that match the application patterns in order to make the compute elements communicate as fast as possible, based on how the application work. So if I'm taking a look on the infrastructure itself, you can see, well, you don't really see, but in the middle you can see the switches, and then all the connectivity that comes from the switches. And then you can see here that those represents the network adapters that sits in every DGX. So there is 8 network adapters in every DGX, and those are connected to the switches, and then the switches create the connectivity among all of the network adapters, and this is how everything connects together. The different components, well, obviously the switch today runs in 200 gigabit per second. We did announce a few months ago the 400 gigabit per second. So actually we're doubling the speed of the network to 400 gigabit per second. And then the new 400 gigabit per second switches are now shipping. It's actually new. Now shipping, every switch has a 64 ports of 400 or 128 ports of 200 gigabit per second. So essentially, if you're building a DGX-based system, just to give you illustration, and every DGX has 8 GPUs inside, one switch like that can connect 16 DGXs together. So there is a huge traffic capacity. Within a DGX, we can find the network adapter, which is in our name, it's the ConnectX, the InfiniBand connectivity, or the DPU, which is a data processing unit, which I'm not sure that we have time to talk about it today, but the DPU, it's actually a new computer by itself. It's a full data center on a chip that can be used instead of a standard network adapter, and it actually brings more computing engines on the network. And I'll talk a little bit about that. One thing that's unique to the InfiniBand network is that this network not just providing networking services or moving data from one node to another node, or one GPU to another GPU, or one CPU to another GPU. The network also brings computing services. The new generation of networks actually include data engines or compute engines on the network itself. And that's become important. And it's become important because in the past, the concept of analyzing data was that we need to move data all the way to the data center, all the way to the supercomputer, all the way to the compute engines before we do anything on the data. And as we're analyzing growing amount of data and have more sources of data, it's not feasible anymore. And actually, instead of moving data to the compute side, we need to move compute to where the data is. And that created edge computing. So we're doing first analysis next to the sensors. We're doing analysis in the car. We're doing analysis where we do experiments, for example, where we're collecting data. We do the first analysis there. And then we're sending the results. And within the supercomputer, we also brought computing engines to sit on the network, so we can actually analyze data as it moves between the nodes, as it moves between the servers. And one example of compute engines like that is an engine that does data reduction on the network. And doing data reduction, it's an important part, for example, is as part of AI training. And instead of doing reductions on the GPU, we're doing reductions on the CPU, which takes more time. And the more nodes you have, the more compute that you have, it's going to take longer and longer time. We can actually perform those operations directly on the network, do it much quicker. So there is engines of doing data reductions on the network. There is actually programmable engines that you can move algorithms to run closer to where the data is. There is engines for doing all-to-all operations on the network and so forth. The network is not just moving data from one side to another side. The network includes ARM cores, the network includes programmable data paths, and the network includes dedicated compute engines that can be programmable. And the new generation of application actually split the work on the GPU, on the CPU, and on the network itself. And it's important to understand it because it actually enables great analysis there. So those are some of the elements on the network. There is the
Gilad, we have 1 minute. Okay.
And we're running out of time, so I'm going to close in 1 minute, of course. And those enable a lot of interesting things to do. To solve, for example, performance isolations. So one of the new capabilities that we brought to the network is to make sure that one application running on a supercomputer will not impact another application performance, which is becoming a big problem. So there's a lot of other things on the supercomputing itself. I hope that we'll have time to talk about some of the computing engines of the network, but we don't have time today. And of course, to talk about new elements of computing that combines, networking that combines computing and networking in a single silicon devices to actually bring programmability to the network, to bring security and isolation. So it's actually creating a new processor to translate or to move the supercomputers to the new architecture of cloud native supercomputing. So I'm going to stop here, Uri. That's where my time's up. If there is interest, I'm more than happy to give more information, of course. And if there is any interest, I'm more than happy to present in other events and kind of cover more information about how to build a supercomputer. So with that, I'll thank you and hope that I'm on time, Uri.